Hey guys, welcome back. We were just talking about inductors, self-inductance, and inductive reactance. We were taking a look at, how a coil behaves when I connect it to a DC circuit, and we talked about the voltage and the current here, and what occurs, just when I change the circuit, right? When I close the switch or open the switch, and it would be the same thing when I, change the voltage, increase the voltage or decrease the voltage. Anytime I change the voltage, it causes the magnetic field to change. Anytime the magnetic field changes, it crosses conductors adjacent to the windings, or, you get the idea. So, this is all kind of hard to understand, okay, guys? And so I've often said that inductance is really kind of like momentum, okay, guys? So imagine an inductor as something that's really heavy and you're trying to move it, okay? It's the electrical equivalent of momentum. Imagine this as a train, okay? And here I go along, the thing's in neutral, it's just running, the train's not moving at all. So current will be like speed of the train, and the voltage will be like the force that the engine is applying to the train, okay? And all of a sudden I put it in gear and I go full throttle, okay? Now, if this thing has no self-inductance, it's super, super light. As soon as I go full throttle, I'll have full speed, okay? But this thing is heavy. It's a train, so I'm going to go full throttle here. We're just going to keep it pinned to the wall here, and the train will start to come up slowly and eventually be running at, whatever speed it can run at based on how much friction there is here, okay? But there's a period of time that even though I've applied a lot of force, there still isn't really much speed, okay? But eventually I get it going, and it's going nice and smooth here. It's the only thing limiting the speed here is going to be the friction of the wind and the tracks and all those kinds of things. And then eventually I'm going to actually, boom, shut the engine right off. Now, just because I've shut the engine off doesn't mean it's going to stop. This thing is heavy. It's really heavy. And so the engine is stopped here, but the train would tend to want to continue to roll for a long time until, whatever energy that I stored in the system over here has come out, and it comes out here, and now it's finally stopped, okay? So imagine an inductor as a device in the electrical, world as a very heavy device. A resistor is a really light device, okay? It has its current limited only by the fact that there's a bunch of friction in the system but no momentum, all right? And so, I didn't draw it, but if I did draw it, if I had a resistor, guys, it would look like this, right? So here's my battery, here's my switch, here's my resistor, right? And if I, plotted this exact same thing here in time, guys, I would have, the drill. I would have no voltage with the no current with the switch open. Eventually I'm going to close the switch. There's my voltage, guys. And then I'm going to open the switch, and my current, there'd be no current here. Right, guys? Be just like that. All right, guys? So, I don't know. Just another way to think about it, and maybe that helps. Maybe it doesn't. I'm not sure. All right, so who cares, right, about inductors in DC? This course is about AC, guys, and so what we care about is how inductors behave in AC. And so I've created this little, some notes here for you, and we'll go over them one at a time. The first note that I wrote down here, guys, is in AC, inductors cause the current to be limited all the time, and it does so because the voltage is constantly changing, right? You guys are fully aware that the voltage is going to go like this, and so that magnetic field is going to be, expanding out, collapsing, reversing, expanding out, collapsing, reversing, expanding out, collapsing, and that changing magnetic field will constantly be inducing a voltage into these adjacent conductors, and that voltage will always be opposing the applied voltage, okay? And so I've got that right here. The changing magnetic field is constantly inducing a voltage into adjacent turns, okay, which is going to oppose the applied. And this current limiting effect is known as inductive reactance, okay? And so if you remember from level 2, guys, inductive reactance is always represented by the symbol XL. Its unit is in ohms, and there's a bunch of different things that limit current in AC. Resistance, inductive reactance, also capacitive reactance, which we're going to learn about pretty soon. Anything that limits current is going to be measured in ohms. And here's the formula for inductive reactance here. XL is equal to 2 pi FL, where XL is the inductive reactance, guys. You know, 2 and pi and 2 and pi. F is the frequency, guys. And, you know, I say guys a lot, but I know there's girls in the class. And when I say guys, I just mean people, right? The non-gender version of the word. F is equal to the frequency in hertz, right? This is supposed to be an F. Inductive reactance in ohms. And L is the inductance in henries. And when we talk about the inductance in henries, guys, students get confused about that. What's the difference between inductance and inductive reactance? Well, every coil has a certain amount of inductance. It's built into it in the factory, guys. So if you take a coil, it has something to do with how many turns it has, what's its diameter, how close the turns are together, what the core material is it iron, is it some other material? You know, there's a lot of stuff that goes into how many henries a coil has, but however many henries it has, and that's built into the factory. It's just like a resistor. If I buy a resistor, its resistance is 200 ohms. That resistance was built into it in the factory, and it doesn't matter what circuit I hook it up to, it'll always be 200 ohms, and there's nothing I can do about it. Whereas the inductive reactance is really, you know, how many ohms it is. How is it going to behave in an AC circuit? Really, and how it's going to behave in an AC circuit depends on how many henries it has built into it in the factory, but it also depends on the frequency of the AC circuit, because if I change the frequency, guys, it's going to change how this magnetic field behaves. It's going to expand and contract more quickly. It's going to be moving past the conductors more quickly, things like that. And so it changes, you know, how good this thing is at limiting current in the AC circuit. And so to practice that formula here, guys, we're going to build a little circuit here just for fun. This is going to be an AC circuit. So here's my AC. Here's my coil. Okay, guys. And just for fun, we're going to say L is equal to 0.16 henries. This is going to be 120 volts. It's going to be 60 hertz, okay? And we're going to see how this thing behaves in the circuit using the formula XL is equal to, 2 pi FL, okay, guys? And so it is going to be 2 times pi times the frequency times the inductance in henries, all right, guys? And so I'm going to find my handy-dandy calculator here. I lost it. There it is. We'll turn it on. Hopefully you can see that. We're just going to actually pound that all in here. 2 times, you have to find your pi button, pi times 60 times 0.16. According to this, it is 60.32 ohms. All right, guys? And now that we know that, that'll actually allow us to calculate how much current would flow, because the current flowing in this circuit is going to be the voltage divided by whatever it is in the circuit that's limiting current. And for today and today only, we're going to pretend that this actual copper in here has no actual resistance, that this thing is strictly 100% inductive reactance, and that the, you know, it's limiting current and behaving like 60.232 ohms, okay? So if I wanted to calculate the current in this circuit, E is going to be I times XL, which means I is going to be E over, XL, and so it is going to be 120 over whatever it is in the circuit limiting current. Let's try that. 120 divided by 60.32 equals 1.9, 89 amps flowing in the circuit. All right, guys. So we're going to stop this one right here, and we're going to learn about RL series circuits, because in real life there are no such thing as circuits that are strictly inductive reactance. They are always at least two things limiting current in the circuit. One is the inductive reactance of the coil, and the other one is the actual resistance of the copper that makes up the coil. And we'll do that in the next video. Okay, guys?